Before we learn the fundamental theorem of calculus, we approximate definite integrals using areas of rectangles. But in fact, we can do one better than that by approximating a definite integral by finding areas of trapezoids. So instead of splitting our interval into subintervals and using rectangles to approximate area, we'll take our interval from A to B, split it into subintervals, and use trapezoids. So you have to remember what the area of a trapezoid is. And the area of a trapezoid is 1/2 the height of the trapezoid. That is the distance between the bases times the sum of the lengths of the bases. And I have a video that proves this formula. In case you need a refresher, you should see that video. Okay, so what we do is we split our interval from A to B into subintervals. In this case, I've split it into 1, 2, 3, 4, 5 subintervals. And we're going to let each of these subintervals be of equal length. And it's very easy to do that. You just take B minus A and divide it by how many you want. In this case, we have 5. So we're going to split this into trapezoids now. And you'll see when we draw the trapezoids that it's going to approximate the area much better than a rectangle would, because it follows the curve more closely. There's not all this excess area above the curve or any area below the curve that's missing. There is some, but not as much as a rectangle. So now we have 1, 2, 3, 4, 5 trapezoids. Let me name these x values. How about x sub 1, x sub 2, x sub 3, and x sub 4. Now, the length of this is the length of one of the bases of this trapezoid, and the length of that is just the length of the other one. Well, this length is f of a, and that length is f of x1. And so we can use this formula and apply it to each one of these trapezoids, and what you'll find is that each one of these bases is going to be counted twice. So in this case, the integral from a to b of f of x dx is approximately equal to 1/2 times the height. This is the height here, and the height in this case, by the way, the height in this case is b minus a over 5. And that's because we have 5 trapezoids. If you had 6 trapezoids, it would be b minus a over 6. If you had 100 trapezoids, it would be b minus a over 100. And that's making each of the trapezoids of equal height. So 1/2 the height times the sum of the lengths of the bases, which is f of a plus f of x1. And that's going to be the area of the first trapezoid. We add to that the area of the next trapezoid, which is 1/2 the height times f of x1 plus f of x2. F of x1 is that length, f of x2 is that length. We add to that 1/2 the height. We're going to look at the third trapezoid, that's f of x2 plus f of x3. We're going to add to that the fourth trapezoid. That's going to be 1/2 the height times f of x3 plus f of x4. And then the last trapezoid, the fifth trapezoid, will be 1/2 the height times f of x4 plus f of b. Okay. Now you'll see that each of these terms has 1/2 the height in common. So this is equal to, factor out the 1/2 the height, and then we have f of a plus, there's f of x1, but there's another f of x1, so plus 2 f of x1. And then here's an f of x2, but there's another f of x2, so plus 2 f of x2 plus, and then there's 2 f of x3's, so 2 times f of x3 plus 2 times f of x sub 4. And then the very last one, there's just one of them, so it's just f of b. Okay. So, in this case we had 5 trapezoids. You find the height of each trapezoid by taking the length of your interval and dividing by how many trapezoids you need to have or want to have. Generally speaking, the problem will tell you approximate using the trapezoidal rule using 17 trapezoids, in which case you would do b minus a divided by 17. Here we have 5, so it's b minus a over 5. We found the area of each trapezoid, but you can factor out 1/2 the height, and that is this again. And then you're going to have this first base is only counted once because it only counts for this trapezoid here. But this base will be counted twice because it's counted for the first trapezoid and it's counted again for the second trapezoid. And that happens all the way down until the last trapezoid where this base is only counted once. So I have 1/2 the height times f of a times 2, or plus 2 times f of x1 plus 2 times f of x2, all the way down to 2 times f of x sub 4 plus f of b. So you can apply the trapezoidal rule without drawing a picture even, so let's do that. Okay, so let's use the trapezoidal rule to approximate the integral from 3 to 7 of x squared plus x dx. Okay, so let's say using 4 trapezoids. So the first thing we might want to find is the height, and the height is going to be 7 minus 3 over 4. That's b minus a over 4. That's 4 over 4, which is 1. So the height of each trapezoid is going to be 1. And so I'm going to have that this is approximately equal to 1/2 times the height times f of 3 plus 2 times f of 4 plus 2 times f of 5 plus 2 times f of 6 plus f of 7. And then we just plug in 3, 4, 5, 6, and 7 respectively here. So this is equal to 1/2 times 1, which is my height. F of 3 is 3 squared plus 3, plus 2 times f of 4 is 4 squared plus 4, plus 2 times f of 5 is 5 squared plus 5, plus 2 times 6 squared plus 6, plus now just 1, we have 7 squared plus 7. And that's going to be a better, whatever this number is, I'm not going to compute it, but whatever this number is, it's going to be a better approximation of the definite integral of x squared plus x from 3 to 7 than rectangles would be. So there it is, there's the trapezoidal rule. Enjoy.